Okay, so as you're kind of finishing up writing those down, we'll kind of talk through these. So we got properties of power. So again, powers from yesterday is just when we have like a base and then that little number, the exponent kind of raised up to the top, and that tells us how many times we're doing something. So there's lots of different properties with that. So these looks like is mostly multiply and divide stuff. So that first one there, product of powers. So multiply with the same base. What you do is you add the exponent. So if these base values are the same exact number or letter, what you do is you just add those powers together. So how that works is like say you had like x squared times like x to the third. Okay, how this works is if this is x squared, that's like x times x, right? Because x squared is like x times x, same thing multiplied. And then x to the third would be like x times x times x, right? Because there'd be three of them. Total, how many x's do you have there? Five of them. So that'd be the same as x to the fifth. So you can see there how you just take whatever, if it's multiply like this, you just take whatever those powers are, add them together, and then that will get your power there. Okay, so that would happen if they have the same bases. So those both have x as the base. Now, the one that gets confused with is the power of a power. So this here, we've got a power, and then on the outside, we've also got a power. So like an example of this, and again, it's that same base value, that b. This would be like, say we had like x squared again, and then outside of the parentheses, we had x to the third. This is a little bit different because what you're doing here, x to the third, or this third here, means you're doing this chunk 3 separate times. So this would be the same as like x squared times x squared times x squared. So if this is x squared, that's 2x's. X squared again, another 2x's. X squared again, another 2x's. So total, how many do you have there? How many x's? Because you got squared, squared, squared. 6 of them, right? Because this would be like x and x, x and x, x and x. So wouldn't that be a total of 6 of them? Yeah, so in that case, what you do, if it's a power of a power, you multiply, but your thought is, I'm taking whatever this chunk is out however many times that outside power is. Does that kind of make sense, the difference between those two? And then the next one, power of a product. So product raised to a power, each factor is raised to that power. So here, both of these values here are the same, so the m and the m. So here, if you had like an a and a b, maybe you had it like, I guess, I don't know how to write this one as an example. Say you had like an x and a y or something raised to like the second power. What you could do is this is the same as x squared times y squared. So if you need to do something where it says like, hey, simplify this out, or do something where you have to solve, if you've got something multiplied by this, it's like both of those are to that power, whatever it is. If this was like a number in here, you could multiply that out, and that would be fine too. Division then, how that works, so if you've got division, so quotient is just divide. So if you've got the same basis for divide, so like b to the m and b to the n, what you do is you subtract the powers. So say I had like, say it was like x to the fourth on the top and x squared on the bottom. What my thought would be there is x to the fourth is x times x times x times x, right? 4 times out. X squared is just x times x. What happens in a fraction when I have the same thing on the top and the bottom? One of them can cancel out, right? So like here, if I've got an x on the top and an x on the bottom, couldn't a set of those cancel? Yeah, and then again, if I got an x on the top and an x on the bottom, can those also cancel? Yeah, so how many am I left with there? 2, so that would be x times x, which is x squared. So how it works is you can always take those powers if the base is the same, and you can subtract those. Next one there is just saying, like, if you had some sort of fraction, so like say it was like, I'll just use xy again. If you've got that, and it's to some power like squared there, it's just saying you can take each individual thing and do it to a power. So sometimes that's helpful in like solving stuff. So like here, this would be the same as x squared over y squared. So just saying you can put the squared with each of those because it's in parentheses there. And then the last one there, anytime you have a variable or a number or whatever to the power of 0, automatically it's going to kick out a 1. So anything to the power of 0 is always 1. And how that works, so say we had something where it was like, say it was like x squared over x squared. Well, here, if we look back at our quotient property, if we have the same bases and it's division, we subtract powers, right? Well, what's 2 minus 2? 0. So it'd be like x to the 2 minus 2, which is x to the 0. And we know if it's the same thing on the top and the bottom, wouldn't those both cancel out to be 1? Should be, right? So that's just another way of thinking about it. But the main thing is if you ever have something, any number, equation, whatever, to the power of 0, it always is going to kick out a 1. Your base just can't be 0, because if it was 0 to the 0, that's just 0, because it's just 0. But does that relatively make sense? Those are kind of the big, main important things. Okay, so then let's look in our packets. The rest should be in our packets now. So here it wants us to solve this out. So we're trying to solve for x here. We got 18 to the 4th times 18x is equal to 18 to the 12th. So what I would do here, so you could take 18, put it in your calculator to the 4th. You could take 18, put it in your calculator to the 12th, get some numbers. But if we multiply 18 out 12 times, aren't we going to get a huge number? Yeah, so instead of doing that, because all of these bases are 18, what I'm going to do is I'm going to look back at my properties here and see if I can figure out which of those properties matches it to see if I can use that to kind of help me solve for x. So here, if I'm looking for something where it's multiply and I have the same bases, that appears to be like our first property here, right? Because don't those have the same bases? And then we've got different powers there, but it's multiply. Here in our thing, we've got the same bases, different powers there, but it's multiply. So same concept. So up there it says, okay, well, whatever our two powers are, it's the same base, and then we just take it and add those values together. So here, if these are all the same base, what we can do is we can just think of it as the powers added together equaling that other power, okay? Because we know the powers are always added together when we have the same base. So now, can't we just solve that for x? Just do like subtract 4 on each side. X would give us 8. Because there, if we had something to the 4th, and it was the same base as something to the 8th, 4 plus 8, wouldn't that give us 12? Yeah, so you don't even have to do like the nasty numbers out. You can just use those properties and go, okay, it kind of follows this pattern. What's it tell me about the powers? Okay, it's add. So we can solve it out that way. Okay, next one there. How many zeros are at the end of the number n is equal to 5 to the 5th, 2 to the 5th, and 32 all multiplied? When n is written as a base 10. Base 10 is just like scientific notation. It's kind of what they're talking about. So here, my thought would be, again, you could do this out on your calculator, 5 to the 5th, 2 to the 5th, and get really big numbers. But if those powers are the same there, I would go up here to my one that's powers that are the same, so it's multiply with powers that are the same, so that's this one here, where it basically shows me that I can take whatever those base values were, and they can be different numbers, multiply those together, and then put those both to that same power. So like here, if I've got 5 to the 5th, rewrite it down here, 5 to the 5th, times, what is it, 2 to the 5th, times 32. If these both have that same exact power, what I can do is I can group together my 5 times my 2, and then have my power of 5 on the outside there because they're the same power, and then I'm just going to leave that times 32 at the back there. And then here, if I do this out, what is 5 times 2? 10. So that would be like 10 to the 5th times 32. Well, 10, if I am multiplying 10 out 5 times, how many zeros are going to be behind that? So like 10 times 10 times 10, 5 times out. How does it work when I multiply by 10s? Well, what's 10 times 10? 100, and how many zeros are in 100? 2. Okay, so I multiplied 2 10s and I got 2 zeros. If I'm multiplying 5 10s, how many zeros am I getting? 5. Okay, so it would basically be like, 10 with, or a 1 with 5 zeros behind it times 32. So without even using our calculator here, this is just 32 with 5 zeros behind it. And really, they just ask us for the number of zeros anyway, so if that's 10 to the 5th, it'd just be 5 zeros. And again, you could do that on the calculator too if you wanted to. Some of the really big numbers the calculator's not going to like. That one would probably be fine because it's not too big, but sometimes the calculator gets weird about it. All right, next one there. Multiple choice English quiz is 2 pages long. Each page has 6 questions. Each question has C possible choices. How many different ways can you complete the quiz if you leave no answers blank? Okay, so they're not talking about like right versus wrong. They're just talking about different ways you could answer these questions. Okay, so let's start with if it's 2 pages long and there's 6 questions per page, how many total questions are there? 2 pages, 6 questions each. 12, thank you. Okay, so 12 questions. 12 questions with C possible. You guys know the W with the slashes with, right? Okay, C possible answers. So this kind of goes to the probability thing that we had from yesterday where we're doing like times to the power. So what you do is you take your number of choices. So here our number of choices is C. You take that and you have that many choices 12 separate times for 12 questions. So it would be to the power of 12. Okay, so your amount of choices goes here, and then whatever number of questions you have goes there, and then that would be as far as we could go because we don't know what that C is. If we knew what the C is, we could go further, but we don't, so we'll just leave it like that. Okay, a couple more here. All right, mass of the Earth is about 5.9 times 10 to the 24th kilograms, right? While the mass of Jupiter is about 1.9 times 10 to the 27th kilograms. The mass of Jupiter is about how many times the mass of Earth? Okay, well, if we need to figure out how many times bigger something is than something else, what we want to do is we want to take those two numbers and we want to divide them. So we're going to take our mass of Jupiter and divide that by our mass of the Earth. So the mass of Jupiter is that 5.9 number. No, mass of Jupiter is the other one. Mass of Jupiter is the 1.9 number. Okay, so we're going to go 1.9 times 10 to the 27th divided by 5.9 times 10 to the 24th. And then what I'm going to do here is I'm going to group together the things with like similar bases. So like here, these don't really have like bases, but they're just regular numbers. So I can group those together. So I'm going to group like the 1.9 and the 5.9 together. And then I'm also going to group together the 10 to the 27th and the 10 to the 24th because those do have the same bases. And then what you can do here with our power stuff, if we have the same bases and it's division, this is like 27 of these 10s across the top, 24 of the 10s across the bottom. So if I've got 27 on the top and 24 on the bottom, how many can I cancel out from top and bottom? I got 27 on the top, 24 on the bottom. How many total can I get rid of top and bottom? 24. So I can get rid of all of those guys, right? And here, if I get rid of 24, what's that leave me with? 3 of them, right? And I can do that because I'm doing, it's basically like 10 to the 27 minus 24 is what that would be. I should put that over a little bit so it doesn't look like it's part of the problem. But yeah, so our powers thing from the previous page tells us when we divide, we can subtract those powers. So if we do that, that would leave us with 3 of them on top. And our bottom, since that all goes away, it would just be kind of like it's a 1 there. And then what I would do is I would just use my calculator to divide out 1.9 divided by 5.9. So 1.9 divided by 5.9 is, it's a gross number, so we'll have to go approximately. So we'll go approximately like 0.322, somewhere in there. And then we'll have that times 10 to the third, because again, those powers canceled out to get it to 3. And then if this is 10 to the third, what you can do is when we multiply by 10, this is like taking this times 1,000. So here we would be going 1, 2, 3 spaces with our decimal, and we're moving it to the right because it's a big number. So that would end us up getting us to 322, approximately. And then that would be times as big is what they were asking. So Jupiter would be 322 times as big as Earth. Okay, and then one more here. So the last one, so a cylinder can contain 3 tennis balls, fits tightly in a rectangular box. What is the percent of volume of the box taken up by the cylinder? Okay, so here this is supposed to be just like tennis balls, and you know what tennis balls come in, those little cans. So here they're saying, I'm going to butcher this picture, but they're saying that there's like a box around that. Again, I'm kind of butchering this picture, but basically like a cylinder box on top of that picture. You get the gist of what a box would look like around that. But there's a box around that tennis ball thing, and what we're supposed to do is we're supposed to figure out the percentage that's taken up by that cylinder compared to the whole box. So our goal here for percent, percent would be figuring out the volume of the cylinder, you guys know what cylinder is, right? Like a can. So the volume of the cylinder over the volume, so would be volume of, it's called a rectangular prism when it's like a box like that, but that would be the total. So our percent is always the part we're looking for over the total, so the part we're looking for is the cylinder out of the total of the rectangular prism. So to be able to do that stuff, to find the percentage, we got to find the volume of each of those things. The volume for a cylinder is pi r squared h, so that's for the volume of the cylinder. Volume for the rectangular prism is length times width times height. Now what gets a little bit tricky here is because we're dealing with like circles and stuff in these tennis balls, I don't think it shows us in the thing, but I think it's supposed to say in there that the tennis balls have a radius of r. I'm going to draw a little picture of this here. So like if we're looking at this box, the top of that box, you've got your little tennis ball inside of there, and the radius of it is just r. They don't say that in the directions, but I think that's probably just a typo on my part. So like here, if we're trying to figure out like the actual dimensions of that box for our rectangular prism, if from the middle out to the edge is r, what is it to the other side? Well, not r squared. It would be r as well, and if we've got r plus r, because we're just taking that part plus that part, what's the full dimension there? R plus r. Not squared, that's multiply. 2r, we got two of them, right? So that dimension that way is 2r. Now if it's a square box here and it's 2r that way, wouldn't we have those same radiuses going the opposite way as well? We would, right? So that top of that box would be 2r by 2r. And then long ways of the box, if we've got three of those tennis, oh Jesus, that's a horrible picture. Look at those tennis balls. That's not one I would buy. If we've got three tennis balls in there and they all have that same radius of r, well again, going this way, wouldn't that be r and r? It would be 6r, because if we're going this way, we got it there, we got it there, and we got it there, so it'd be like 2r, so r and r, r and r, r and r. It would be, oh shit. Okay, well, I guess we're finishing this tomorrow. Sorry, I wasn't watching the time.